Yeah, here is the experimental and numerical study for the combustion and soot formation of the biojet fuel. My name is Zhan Xiao, and my supervisor is Dr. Tian Bo and Dr. James Jokas. Here is the content. So my biojet fuel shoot program includes 3 parts. The first part is biojet fuel introduction, and compare the biojet fuel and normal jet fuel. The second part is PIV system and PIV experiment. The third part is co-flame code experiment described. So the first part, the biojet fuels. The biojet fuels include many different kinds of biojet fuels, such as Fischer-Tropsch FT synthesis using natural gas coal and local cellulosic biomass as feedstock, hydroprocessing of renewable material from plants such as plant and soil and grasses. The third one is the hydroprocessed renewable jet HRJ. Is made from used cooking oil, alcohol to jet ATJ, and sugar to jet STJ. STJ and its jet term alcohol algematization is converted from a variety of different chemicals such as methyl, ethyl, bentanol, and a long chain of different fatty-based alcohols. Hydroprocessed ester and fatty HEFA oil and fats from both plants and animals, including vegetable oils and other animal oils. Here I will describe the ratio about shoot point for biojet fuel applies as a function of blending. You can see the HEFA over jet A fuel ratio and FT over jet A1. Jet A and ATJ over Jet A. So HEFA is the highest shoot smoke point, then FT, then ATJ. Here is the shoot value fraction profile along the flame center line for biojet fuels. You can see that JP5, JTA, and JP8 are jet fuel, the normal jet fuel, and ATJ, FT, SPK, and HEFA can be linear are biojet fuel. So the jet fuel are more shoot value fraction than biojet fuels. The JP5 are larger than JTA, larger than JP8. So the ATJ are larger than FT, SPK, larger than HEFA for the biojet fuel shoot value fraction. So this is the NVPM emotion characteristics of the aircraft gas turbine engines burning biojet fuel blends. So it also includes the blended fuel, FT, SPK, HEFA, SPK, SIC, SPK over A, ATJ, SPK, JP8, JTL, FT, JTL, FT, and JP8, CTL, FT, Jet A1. So it can be described the aromatic, sulfur content, hydrogen content, delta H, and H over C. So I will describe about aromatic. The particulate matter PM include aromatic. As the formation of the first ring is circumvented aromatics from aromatic hydrocarbon, pH. As pH formation is highly correlated to shoot formation. The aromatic has not a linear relation with the carbon number. So I will also describe the global jet NVPM emotion inventories. The global jet PM mass emotion inventories offer assignments on annual biojet NVPM emotion. Evaluate the magnitude of NVPM mass emotion. The aromatic hydrocarbons in fuel are critical NVPM processors. Aromatic free property of biojet fuel to NVPM mass and number emotion reduction. Here is alkanes and alphanes line about normalized mechanism shoot formation. The high temperature shoot formation, the high reactant temperature lead to a high shoot formation. Alkanes are more sensitive to the temperature change than alkanes. So the shoot oxidation may lower by higher reactivity temperatures. Here is another picture in the right-hand side. The frequency of JTA1 and HEFA blinds in the aldo. The next one is the HEFA and the JTA1. The second one is aldo and P85 in JTA1. The third is aldo and P85 frequency in HEFA. The fifth part is the PA5 with AR and PA5. We can say that normally in the first one, the JTA1 is more frequency than HEFA. So the second one in the aldo time is the JTA1 is the frequency is higher than P85. So in the aldo is larger than P85 in HEFA blind. So also in HEFA blind, the P85 with AR in fringe legends less than 1 is higher than P85, but over the 1, especially in 1.5, as that fringe legends is smaller than P85. So in the ground idle condition, using JTA1 field has the highest high field frequency. You can see that in the first part, JTA1 have the higher frequency than HEFA. In the second part, in the P85, the JTA1 is less than HEFA. In the second part, aldo is less than P85. In the fourth part, HEFA part, the aldo is less than P85. In the fifth part, P85 is less than P85 with air. So here is a different sampling temperature are denoted with using different color. We can see that like JTA1, HEFA, and JP8, JTL, JP8, CTL, and JP8, HRJ, JTA1 with FT. JP8 over FT, JP8 over JTL, JP8 over CTL, JP8 over HRJ, JP8 over TRJ, JP8 over FT. So now in the second part, I will describe the particular image valorimetry. The particular image valorimetry PIV use Davis-10 software. The camera uses the imager CX file. Camera has a linear resolution 2440 times 2040. The Davis PIV kit has options to combine 64 times 64, 32 times 32, 16 times 13, and 8 times 8 pixels as an integration area. If we choose 32 times 32 pixels to form an integration area and want to cover a total probe volume roughly 10 times 30 centimeter, laser belongs class 4 laser devices. Here is a calibration PIV example. Oh, it's dirty for the measurements. We can see. Seriously, the dirty x over V is 5 times 0.0015 over 32 over 0.05 is 5.68 milliseconds. The DT is adjusted by altering the frame rate and consequently the laser repetition rate. Here the formula is for calculate the 32 times 32 pixels to form an integration area. So from this we can say that 100 times 2440 over 32 is 1.31 millimeter. So 1.31 millimeter can choose the roughly totally probe volume roughly 10 times 10 centimeter. For the PIV integration, the common integration size for PIV is 32 times 32 pixels. The cross-correlation process normally has 50% overlap. Each integration window has 8 to 10 particles. So we can see experiment setup for PIV. The PC and Davis platform, the frame grabber, the camera, the signal generator, and ND-YJ lasers. 532 nanometers, 30 millijoule plus max. We can see that the laser is from the laser sheet to the mirror to the probe value for the refractive index matching liquid and cover with the tank. Here is tank and pump for PIV experiment picture. So in the third part, we will describe the conflict codes. Why we should use the conflict code, not the other code. The conflict code can calculate mass, momentum, energy, gas phase, chemical species. The programming language for the conflict code is Fortran 90 MPI. Requirements are Intel compiler. The Linux workstation is also used for the conflict code. The true formation in linear different flame is also important for the co-frame codes. We can see that this is a low Renault number co-frame code results in same with the experiment. So we can see less than 80 Renault number is the low Renault number of the co-frame code is similar with the experiments results. The conflict code results in larger than 80 Renault number is higher than experiment results. Here is the alkane's flame speed. We can see that at same temperature and pressure condition, methane is the lowest flame speed. Ethane is the largest. I will describe another model used in the conflict codes. So it's about conjugate heat transfer (CHT) model. The CHT is a model is a mesh model in conflict code. CHT is implemented by the harmonic method to model the heat transfer between the fuel streams and solid fuel tubes. CHT is also a model in airstream and fuel tubes. So we can see here is an example to like Model 1 and Model 2. So Model 1 is no CHT and Model 2 is with CHT mesh model. CHT simulation means part of the field tub included in the computational domain. Here is another example with CHT and without CHT example. So the left hand is no CHT in the right hand picture, and the right panel is with CHT models. The shoot prediction lower sensitivity to alpha can be explained by the difference in shoot formation. Mechanism on the wings. pH adsorption is the predominant mechanism on the wings for the CHT model on the right-hand side, the making shoot formation for the wings less sensitive to alpha. In contrast, without additional pH prediction, HAC surface growth remains dominant on the wings for the no CHT model on the left-hand side. To use the no CHT model can improve the prediction by increasing alpha. Here is an example of CHT temperature mass model in the left-hand side, and the right-hand side is shoot wing picture in the experiment. An experiment of C2H4NH3 pH model used in conflict code. It includes 149 species and 1376 reaction for the new kinetic model. So it's used the chemical software offset flow flame model. So one of the important aromatic field is NH2. It can be determined the chemical effect NH3 on the flame. The conflict code can also be run the C2H4NH3 pH model. Here I will describe another mechanism, Crick mechanism. Crick is an Italian group, basically in Milan. So over 8,000 reactions and more than 250 species. The thermochemical data for most species were obtained from the chemical thermodynamic database. All numerical simulations were performed with the open small code. The small hydrocarbon species such as alkanes, allynes, dienes, and the large hydrocarbon species, linear and branches alkanes such as N-hyptane, N-decane, N-dodecane, also octane, hydroalkane aromatics. The alcohols and oxygenated species and hydrocarbon mixtures can also be determined in the Crick mechanism. Here is I dropped the shoot detail about conflict code in TechProt. Here is a shoot experiment use machines such as shoot volume friction FV and primary particle diameter DP can be measured by laser-induced incidence TIRELI system. FV and DP measurements need more than 500 times experiments. The shoot temperature can be measured by spectral shoot emotion SSE technique. Flame temperature can be measured by repeat thermocouple insertion RTI apparatus. TEM imaging and Raman spectroscopy can be measured to shoot particle imaging. The transmission electron microscopy TEM imaging demonstrates the higher abundance and the larger aggregate size of pptx. We can describe before in the part 1, left panel values and ground idle condition in the right hand panel. So now I will describe about my future work. In my future work, I will come to UK, China Low Carbon College, Shanghai Jiao Tong University for the lab with this September. It may be get some experimental shoot process results, and it will be described. We also describe in the future confirm code results. I will also choose some design and chemical kinetic models for the future in the conflict code design. So here is my report, and this is the reference of the provision report for the presentation. Here are all my described in the presentation. Thank you.